In this video, we talk about the different types of formula that can be used to represent organic molecules. The first that we'll discuss is the molecular formula. This is the one that is probably the most widely used. If I ask you for the formula for glucose, you tell me it's C6H12O6. I'm sure you wouldn't stop to think about drawing it, you just tell me C6H12O6. The molecular formula of a compound tells us the type of elements that are present and the number of atoms of each element that is present. While they do tell the makeup of the compound, they don't give a lot of information because they don't tell us how these atoms are linked together. One way that we can determine the molecular formula of a compound is by using a technique called mass spectrometry, which we'll talk about in another video. If you know the general formula for a particular homologous series, then you can also determine the molecular formula for that compound. Let's say you know a compound is an alkane and you know that it has 5 carbons. Using the general formula for an alkane, which is CnH2n plus 2, we can write the molecular formula, which would be C5H12. From the formula, we know that we have 5 carbons and we have 12 hydrogens, but we don't know exactly how these carbons are linked together. Do we have a straight chain compound? Is it branched? If it is branched, which carbon is this branch on? The next type of formula is the empirical formula. The empirical formula of a compound shows us the smallest whole number ratio of the elements that are present in this compound. We can determine the empirical formula of a compound experimentally using something that's called combustion analysis. But if you already know our molecular formula, we can determine the empirical formula by finding the ratio. How do we do that? We find the ratio by dividing all the numbers in the subscript by the smallest number in the subscript. Let's think back to the molecular formula of glucose. That was C6H12O6. The smallest number in the subscript is 6. So if we divided all those numbers in the subscript by 6, the empirical formula would be CH2O. Empirical formulas are important if you just want a quick glance of what elements are present in the formula. Let's do another one. On the previous slide, you'd have seen a compound benzene, which has the molecular formula C6H6. The empirical formula therefore must be CH. There are some compounds whose empirical formula and molecular formula are the same, meaning that the ratio of the elements in the molecular formula is already in its simplest form. Some examples are water, H2O. We couldn't break this down any further. The smallest number is 1, and we know anything that is divided by 1 would give us the same number. Another example of a compound whose empirical formula and molecular formula are the same is carbon dioxide. Now, these are not organic compounds, but you will come across organic compounds that have the same empirical and molecular formula. Let me just give you one example: methane, which is CH4. All the remaining types of formula are some type of structural formula. First is the displayed formula. The displayed formula shows how all the atoms are linked together. These will be simplified drawings because we'll just be using straight lines. But of course, with knowledge of the valence shell electron pair repulsion theory, we could actually use different types of lines to show what axis each bond lies on. Now let's think about glucose once again. So its molecular formula C6H12O6. We saw its molecular formula CH2O. The displayed formula would look something like this. This is the structure of alpha glucose. Even though alpha glucose and beta glucose have the exact same molecular formula, the way how the atoms are arranged in space is different. And that highlights for us one key importance of using a displayed formula. The displayed formula, again, is just a diagram, but it shows us how all the atoms are linked together. We need it for isomers. Isomers all have the same molecular formula but a different structural formula. So the displayed formula will help to show the differences in the structure. Do you know what compound that is on the right? That's also glucose. Glucose can exist as a ring structure. Now, simply writing the molecular formula would not indicate that at all. When you write C6H12O6, it could be in one of many different orientations. So once again, the displayed formula is important because it shows exactly how these atoms are bonded to each other. The next type of displayed formula that we can use is a condensed formula. We say it's condensed because we don't show the bonds in this structure. The condensed formula simply shows the group of atoms that are attached to each carbon. I'll use the example of propane to show you how the condensed formula could be written. This is the displayed formula of propane. The condensed formula. For the condensed formula, we focus on each carbon in the chain and then we'll write what is attached to that carbon. So we'll start with the first carbon that's on the left. We'll start with the first carbon that's on the left, and that carbon has 3 hydrogen atoms bonded to it. So we'll start with CH3. The carbon in the middle is bonded to 2 hydrogens, so we'll write CH2. The final group that's on the right has a carbon which is bonded to 3 hydrogens. When writing condensed formula, we need to be able to represent groups of elements that appear as a branch. To do this, we use brackets. Here we have the displayed formula of methyl propane. To write its condensed formula, let's start from the end to the left. So we have a carbon which has 3 hydrogen atoms attached. Next we have a carbon with 1 hydrogen, but it's also bonded to another carbon which has 3 hydrogens. This could easily seem as if the chain is continuing, so to ensure that the viewers know that this is a branch, we place it in brackets. Then finally, we'll add the other group that's to the right, and there we have a carbon bonded to 3 hydrogen atoms. The final type of formula that will be discussed in this video is a skeletal formula. The skeletal formula does not show carbon and hydrogen atoms and gives us the backbone of the structure. But this formula will be using a series of lines and bends. We just saw the displayed formula of propane. It had 3 carbons. The skeletal formula of propane looks like this. Every open end of a skeletal formula represents a CH3 group. Every bend represents a CH2 group. And here we have another open end, which means, of course, another CH3 group. Now, this works perfectly for alkanes, but of course, we do have other functional groups. To represent these functional groups, we have to use 2 lines if we need to show a double bond, and if we're going to have a carboxylic acid group or an alcohol group, aldehyde group, carbonyl group, if there's an oxygen within the structure, then we have to use the symbols for those elements. Here we have the displayed formula of 1-butanol. To draw its skeletal formula, let's start with our first line. This would represent carbons 4 and 3. This would include carbon 2, and once we add that other line, we have our carbon 1. Because at the end of this carbon, we have that OH group, we have to write it in. Here we have the displayed formula of propene. Once again, we have 3 carbons, but because there's a double bond, we must show that in the structure by using 2 lines. If this was an alkane, at the open end we would have CH3. Because the double bond has been added, we no longer have 3 hydrogens there, we only have 2. And in the bend, where it's usually CH2, the fact that this carbon has a double bond also means we can now only have a CH. Once we add functional groups to our skeletal formula, we have to adjust the number of hydrogens appropriately. You should be able to interpret skeletal formula as well. Open end CH3, bend CH2. We have a bend, but there are 2 things that are attached to that bend. So instead of having a CH2, that additional bond means that we can only have CH. We do have a branch, and remember when writing condensed formula, that branch must be represented with a bracket. Then finally, we have another open end, which means we have CH3. And that is it for the different types of formula that we can use to represent organic compounds. A reminder, we have molecular formula, and this shows the exact number of atoms of each element present in the compound. The empirical formula, which gives us the smallest whole number ratio. We have different types of structural formula. Displayed formula, which shows how all the atoms are arranged. The condensed formula, which doesn't have any lines, it just shows how groups are attached around each carbon. And finally, the skeletal formula, which is just the backbone of the structure. Carbon and hydrogen atoms are not drawn in.